Hello, my name is Gerez. I'm a PhD student at the Mechanical Engineering Department and member of the New Dexterity Research Group in the University of Auckland, New Zealand. I'd like to thank the IEEE RAS site for this opportunity to present in the IROS2020 workshop on humanitarian robotics. Today I'm going to present our work that is a hybrid wearable exoskeleton glove equipped with variable stiffness joints, abduction capabilities, and a telescopic thumb. This presentation is divided in 5 sections. I'll start by introduction, then go through objectives, designs and modeling, experiments and results, and then finish with conclusions and future directions. According to the World Stroke Organization, stroke is the leading cause of death and disability worldwide. Approximately 1 in 6 people will suffer a stroke in their lifetime, and weakness of arms and hands is one of the most popular effects, reaching more than 3/4 of stroke survivors. The rehabilitation process of impaired people highly depends on the repetition of movements performing activities of daily living, such as flexion and extension of the fingers, and abduction and adduction of the fingers and thumb, which is required in more than 50% of the grasps executed daily. The quality and stability of grasps are directly related to the hand's ability to constrain efficiently the object motion. An effective grasp is characterized by the ability of the hand to withstand external disturbances while maintaining stable object contact. In general, a hand can grasp a given object in multiple ways. The number of contact points and their distribution while grasping an object give a good measure of the grasp quality. Geometrically, the quality of the grasp is equivalent to the radius of the largest ball centered at the origin of the wrench space and fully contained inside the grasping area. Thus, methods that better distribute or increase the number of contact points between the hand and the object improve also grasp stability. Multiple hand exoskeletons have been proposed over the last years to assist patients with hand impairment during physical therapy or to augment the capabilities of health users. Although the robotic exoskeleton gloves currently found in the literature can assist impaired people, they still have limited dexterity. Most of the devices cannot replicate all the hand motions performed during activities of daily living. Finger abduction is one of the most important motions that the majority of soft robotic gloves cannot execute. The figure shows an example of a robotic assistive glove developed by the New Dexterity Research Group. This design allows flexion and extension of the fingers but does not assist the user in finger abduction or opposition of the thumb. For this reason, in this study, we propose the design of an assistive device to restore or improve the capabilities of the human hand. The assistive exoskeleton glove must be able to assist the execution of abduction motion of the fingers, opposition of the thumb, flexion and extension of the fingers, and ensure stable grasps, and the device must be wearable. The proposed device is composed of 2 main systems, the soft robotic glove and the control unit. The control unit is composed of 5 Dynamixo XM430 motors, 2 mini air pumps, 3 solenoid valves, 1 microcontroller, and 1 vacuum pump. A smartphone app is used to trigger the execution of the selected grasping motion. The total weight of the robotic exoskeleton glove is 1 kilo and 300 grams, while the glove alone weighs less than 300 grams. The soft glove system of the device consists of a glove, a tendon-driven system, a pneumatic system that is composed of 4 soft actuators, and 5 laminar jamming structures. The tendon-driven system has a tendon connected to each of the tendon termination structures and an extra tendon that is connected to the thumb's interphalangeal joint region, facilitating the execution of the position motion. The soft structures are used for 3 different purposes: to perform abduction, adduction of the fingers, increase grasp stability by implementing an extra thumb structure, and to change the bending profile of the fingers. 3 of the pneumatic chambers are connected to the region between the fingers, allowing for the execution of abduction, adduction motion of the fingers. Another soft actuator was designed to act as a telescopic extra thumb that participates in the grasping tasks, increasing the area of the contact patches between the hand and the object and increasing both grasp efficiency and stability. At the back of the glove, 5 laminar jamming structures were added to adjust the stiffness of the joints and to perform a passive extension of each finger and keep the hand in its natural zero-effort position. A flex sensor is located at the index finger and can be used to control the motion of the exoskeleton glove. The soft telescopic extra thumb has been designed to increase the stability and quality of the grasps being executed with the proposed soft exoskeleton glove. The soft telescopic extra thumb actuator is based on a urethane rubber smooth-on VitaFlex 40. The foldable structure was designed in such a way that it does not influence grasps that do not require an extra thumb due to its small thickness and telescopic behavior. The round shape of the actuator was chosen so as to maximize the size of the objects that could be grasped by employing the actuator. The actuator operates at a pressure of 20 kilopascals and weighs only 18 grams. It is 10 millimeters thick and 8 millimeters long. The manufacturing process of the telescopic actuator involves 3 different molding steps as shown in the figure. Initially, the foldable part and the base layer of the actuator are fabricated. The base layer is 2 mm smaller than the upper part in all directions, so that they can be molded together. After both parts are cured, a third mold is used to combine the upper part and the base part layer, filling the remaining gaps between the 2 parts and bonding them together. These techniques avoids leakages and deformations in the actuator. The video shows the operation of the device. Using a smartphone app, the user can select which motions should be executed. The different motions can be chosen separately, according to the user's needs. The user can combine different motions, for example, full grasp with abducted fingers or tripod grasp with the extra thumb inflated and the jamming structures activated. As can be seen, the inflatable extra thumb helps to increase the number of contact points between the robotic glove and the object. The soft laminar jamming structures at the back of the fingers were designed to achieve multiple stiffnesses by applying pressure gradient to the system. The flex sensors located at the index finger can be used in order to trigger the desired function when a set bending angle is reached. The first experiment was conducted to evaluate the soft actuator's ability to execute the abduction motion. This experiment focused on the amount of the abduction force that each mechanism can exert, and on the values of the achievable abduction angles. The abduction force experiment involved the application of pressure to the soft actuator while employing rigid lateral walls to constrain its lateral motion. A calibrated force sensing resistor was placed between the actuator and one of the walls to measure the abduction force that the actuator can exert. The maximum force obtained was 15.8 newtons at a pressure of 130 kilopascal, which is within the range of abduction forces that the human finger can exert. Also, the abduction angle experiment measured the finger abduction angles wearing the proposed hybrid robotic glove. The abduction angles are similar to the values found in the literature for safe abduction of the human fingers, approximately 25 degrees for all fingers and 70 degrees for the thumb. The second experiment assessed the fingertip force exertion capabilities of the proposed soft robotic glove and how the tendon-driven system's performance is improved by employing the jamming structures. The fingertip forces were recorded using a setup containing a hand mount and an indexing plate with different angle positions. The fingertip forces were acquired for angles from 0 to 120 degrees. A dummy hand wearing the soft assistive glove was used to conduct experiments. The maximum force exerted at each angular position was obtained before the fingertip slipped away from the force sensor. The maximum force exerted was 13.8 newtons at 90 degrees when the robotic glove was unjammed, and reached a maximum force of 12 newtons at 45 degrees when the jamming structures were activated. The required force to grasp objects during activities of daily living do not exceed 10 to 15 newtons, and the pinch forces required to execute most of daily life tasks are lower than 10.5 newtons. The results also demonstrate that the jamming structure is capable of increasing the maximum fingertip forces at small bending angles if compared to the unjammed structure. By exerting higher forces at small bending angles, it is possible to improve grasps with the fingertips, for example, pinch grasps and key grasps, and efficiently execute the desired task, resulting in less finger reconfiguration. The third experiment analyzed the bending profile of the index finger in three different modes: natural motion, A, assisted by the robotic glove without the jamming structure, B, and assisted by the robotic glove employing also the jamming structures, C. The experiment's goal was to verify the effect of the jamming structures on the finger configuration during grasping. A camera was placed perpendicularly to the hand, and a point tracking algorithm was used to track the position of the joints while bending the finger. The results demonstrate that when the robotic glove is unjammed but motor driven, the device can impose a bending profile angle similar to the natural motion. When the jamming structure is activated, the motion of the joints are reduced and the motion of the base joint is increased. Therefore, the jamming structures can be used for handling objects that require fingertip or pinch grasps. The third experiment focused on evaluating the effect of the soft telescopic extra thumb on grasping objects. In total, 14 different objects were grasped. After grasping each object, the area of the polygon generated by the geometric center of the contact region was calculated to be used as input to the grasp quality measure. Pictures were taken after each grasp perpendicularly to the hand palm to determine the area of the polygon generated by the contact points between the objects and the robotic glove. Two different scenarios were analyzed, considering the contact points at the extra thumb and considering only the contact points generated by the 5 digits. The figure illustrates the grasp quality measure calculation for the baseball ball. The ratios between the areas of the polygons in both scenarios for all objects are reported in the table. The results demonstrate that the inflatable extra thumb increases considerably the grasp quality. The average improvement of 75% in the grasp quality can validate that the use of the soft structure in the exoskeleton glove improves its overall performance. However, the high percentages presented could be an overestimation, as for some objects the real grasp quality improvement could be lower due to different grasp types and strategies involved. This improvement may be more significant for impaired people with limited mobility of the hand, since the extra thumb will increase their stability and ability to execute good grasps. In this study, we presented a hybrid soft exoskeleton glove that combines a tendon-driven actuation system and soft pneumatic actuators. The device facilitates the execution of the abduction-adduction motion of the fingers and the thumb, and it improves grasp stability by increasing the area of the contact patches between the grasped object and the glove. A series of experiments demonstrate that this hybrid solution can enhance the grasping capabilities of the users, offering robust grasping with a lightweight and soft design. All exoskeleton glove designs, electronics, and code are disseminated in an open source manner to allow replication by others. More information and the links to the files can be found at the following URL: newdexterity.org/exogloves. With the support of the IEEE ROS Site grant, we have participated in the 2020 Hackaday Challenge, which is an international open source design competition. We won the award of the Best Assistive Device in the United Cerebral Palsy Los Angeles category. This achievement allows us to further disseminate our assistive gloves and improve them based on the feedback of users. If you have any questions, please do not hesitate contacting me. Thank you.